want to do is I want to show you how to do numbers 1 and 2 using the t.test function, but the problem is that you have to come up with a data set that has all the different statistics and parameters that you want it to have. So let's say I want to find two samples, and the two samples that I have are going to be I want them to have a sample mean of 10, a sample standard deviation of 2.1, and I want to have 15 data points. Okay, so what I'm going to do is I'm going to go to R, and I'm going to call our data set, let's just call it x1. Okay, so x1, and I'm going to pick 15 data points from a normal distribution with mean 10 and with standard deviation of 2.1. And so what this is going to do is it's going to give us 15 data points. And this 15 data points is not exactly what we're looking for because these are random data points. They're not going to have a mean that's going to be exactly 10. It'll be close to 10, but not exactly 10. Likewise, the standard deviation is not going to be exactly 2.1. It'll be close. In this case, it's 1.6. It's not even that close. That's because it's such a small sample size. The way that we can fix this, though, is we can go through and we can kind of mess with this data in a certain way. We know that there's a kind of a dictionary to go from any set of data to make it standardized. And once it's standardized, then you can kind of unstandardize it and give it whatever mean and whatever standard deviation you like. So that's exactly what we're going to do. So what I'm going to do first is I'm going to shift everything so that it has a mean at 0. So I'm going to pick x1, and from every value in this set x1, I'm going to subtract the mean of x1. So this is going to give us a new set of data, x2, and this new set is going to be symmetric about the origin. So if I were to look at the mean of x2, I should get 0. And what this is saying is that it's actually 0 up to 16 decimal places. So it's not exactly 0, but it's basically 0 for all intents and purposes here. So if I were to find the mean of x2, and if I were to round to, say, 10 decimal places, you get 0, right? You have to go to 16 decimal places or more to get a significant value. So anyway, so now it's all centered around 0. What we're going to do then is I'm going to define, now that it's centered around 0, let's change its standard deviation. So what I'm going to do is I want its standard deviation to be 2.1. So I'm going to multiply all the values by 2.1, and I'm going to divide all the values by the standard deviation of x2. Okay, so that'll give us a new set of data, x3, where x3 is again 0, in this case up to 15 decimal places, and the standard deviation of x3 is 2.1. Okay, so x3 is the set of data that we were looking for. So that's where we have a mean of 0, again up to 15 decimal places, and a standard deviation of 2.1. One final step, though, we don't want a mean of 0, we want a mean of 10. So what I'm going to do is I'm going to take all the values in x3, and I'm going to add to it 10. And now we've done it. Now x4, that data set right there, is going to be our data set that's going to have a mean. So our mean of x4 is going to be 10. Our standard deviation of x4 is going to be 2.1. We have 15 values in that set. So that's a way to kind of reverse engineer a set that has these properties. You know, the sample size is 15, the mean is 10, and the standard deviation is 2.1. So what I'm going to do is let's do that again for these other parameters. So let's say I want to pick 15 values. So again, n2 is 15. So here I'll use y. So y1 is going to be, I'm going to pick 15 numbers from a set with mean 12 and standard deviation 2.3. So it's going to be y1. And again, it's not going to have exactly a mean of 12, and it's not going to have exactly a standard deviation 2.3, but we'll fix it. Y2, what we're going to do is we're going to shift everything so that it has a mean of 0. So we're going to take y1 and subtract the mean of y1 from all those, so that the mean of y2 is going to be 0 up to however many decimal places. We're going to fix the standard deviation. So I'm going to take y2, multiply by 2.3, divide by the standard deviation of our previous set y2, and now the standard deviation is going to be 2.3. Okay, and then finally y4 is, we're going to take all the values in y3 and we're going to add to them 12 because we want to have a mean of 12. Okay, so now we have our two data sets, x4 and y4, and now we can run our the two-tailed t-test for those data sets, and we end up with all the values that we wanted before, right? So we had our test statistics. So just going back to our previous two videos back now. So going back to two videos where we did, or however many videos back, where we went through these examples, these are all the values that we found. T was negative 2.4871. We had a p-value of 0.01916. We had a 95% confidence interval. This told us the sample means of our two samples. Okay, so this is a way to kind of reverse engineer all the stuff that we wanted. So this was our two-tailed test. So we rejected the null hypothesis, and then our 95% confidence interval we found right there, from that negative 3.64 to negative 0.352. Okay, and we can do the same for number 2. Okay, so we can do the same for number 2. One thing that I should actually add here, this isn't, what I just said isn't quite right. What we want is, this was a pooled t-test, so we're going to assume that these two samples, or these two underlying populations, have equal standard deviations and therefore equal variances. So if I write var.equal equals true, var.equal equals true, we get almost the same values. It's the same test statistic. The degrees of freedom is slightly different. The p-value is slightly different, right up to 5 decimal places, but it's basically the same. And we end up with basically the same confidence interval. It's actually so close that I didn't even realize the first one was wrong. Okay, this is actually the right confidence interval that we ended up with. The negative 3.6473 to negative 0.3528. Okay, so anyways, that is how that works. So if you assume that the standard deviations are equal, you have to add in that extra component there. But they're going to be pretty much the same result whether you assume the standard deviations are equal or not. Okay, so that's how that works.